Welcome to the Severe Weather Analysis for Darwin, Australia. Today is Monday, March 2nd, 2026. We are going to dive deep into the atmospheric conditions that developed this morning and what they mean for this afternoon's severe weather potential. If you find this analysis helpful, please like and subscribe to support continued severe weather analysis. Let's start by looking at this morning's atmospheric sounding from Darwin at 9 a.m. local time. We are seeing a typical tropical setup for early March, with warm, moist air near the surface and a complex wind profile aloft. The temperature profile shows a steady increase with height, indicating some stability in the lower atmosphere. The dewpoint trace reveals abundant moisture throughout the column, which is what we'd expect in the tropics during late summer. Notice the wind barbs on the right side of the diagram. They show the wind direction and speed at different altitudes, and we can already see some interesting shear patterns developing. The red temperature line and green dewpoint line are telling us there's energy available if parcels can overcome the initial resistance near the surface. Now, here's where things get interesting. As we move into the afternoon with solar heating, we need to see how this environment transforms. The morning sounding showed some constraints, but the enhanced plot comparing morning and afternoon environments tells a crucial story. With surface heating expected to warm the boundary layer, we are looking at the potential for parcel lift. The atmospheric profile shows mixed stability. There are layers that could support deep convection if the right trigger occurs. The wind shear structure visible in the parcel paths suggests that any storms that develop could become organized. The key tension here is between the available energy, that pink shaded area representing Cape, the fuel for storms, and the blue shaded area representing the cap that's holding it down. As the afternoon unfolds and solar heating progresses, that cap could weaken, allowing parcels to break through and tap into the substantial energy below. Let's examine the hodograph, which shows how wind direction and speed change with altitude. This diagram is crucial for understanding storm motion and potential severe weather impacts. The hodograph shows a relatively compact shape, indicating limited wind shear magnitude throughout the column. What we are seeing is directional shear. The wind direction changes with height, but the overall speed profile is weak. The 0 to 6 kilometer bulk shear appears minimal, which significantly constrains supercell development and organization. Without strong shear, any storms that form would tend to be air mass thunderstorms rather than organized severe supercells. The right mover and left mover vectors, shown as stars on the hodograph, would indicate the direction any supercells would track, but given the weak shear environment, the distinction becomes less meaningful. From an operational perspective, emergency services should recognize that while scattered convection is possible, the severe weather threat from organized supercells producing widespread damaging winds is substantially reduced compared to higher shear scenarios. The Brunt-Väisälä frequency profile, or n-squared profile, reveals the atmospheric stability structure at different altitudes. This tells us about the potential for downdrafts and the environment's ability to support or suppress vertical motion. The profile shows variable stability through the troposphere, with some layers more resistant to vertical motion than others. In the mid-levels between 2 and 5 kilometers altitude, we can see the stability structure that would influence how deep convection develops. The downdraft potential, which depends on both the stability profile and the moisture content, appears moderate rather than extreme. With the modest lapse rates and available moisture, any downdrafts would be partially evaporative, reducing the extreme microburst potential compared to very dry environments. Hail growth would be supported by the stability structure if storms become sufficiently intense, but the shear constraints we've already identified limit the ability of storms to reach that level of organization and severity. The overall implication is that while the atmosphere isn't hostile to convection, the ingredients for extreme severe weather, particularly for long-lived, organized supercells, are significantly limited. Looking at tomorrow morning's ML forecast at midnight local time, we are expecting mixed layer Cape around 797 joules per kilogram with surface-based Cape at 1347 joules per kilogram. The shear is essentially zero at 0.0 meters per second, which dramatically limits severe weather potential. Cloud base sits at just 23 meters above ground level. That's extremely low and would indicate fog or stratus conditions. Both SCP and STP indices are 0.0, confirming that organized severe weather is highly unlikely tomorrow morning. We are looking at a much more benign setup compared to today. By tomorrow afternoon at 6 p.m. local time, the ML forecast shows Cape increasing slightly to 712 joules per kilogram, with surface-based Cape holding steady at 1331 joules per kilogram. The critical factor remains the 0.0 meters per second shear. This complete absence of wind shear is the primary limiting factor. Lapse rate between 700 and 500 hectopascals is steep at 51 degrees Celsius per kilometer, supporting instability, but without shear, any convection will be disorganized and short-lived. Cloud base remains very low at 23 meters. STP and SCP stay at 0.0. Storm mode would be disorganized convection or pole storms, isolated cells with no tornado threat, no hail threat, and no significant wind threat. This is a completely different picture from today's setup. Examining the evolution of these parameters throughout the forecast period reveals important timing patterns. CAPE shows a modest increase from early morning through the afternoon period, peaking in the afternoon before declining slightly by tomorrow. The shear profile, however, shows virtually no variation. It remains at very low levels throughout the entire forecast window. This is the fundamental constraint limiting severe weather potential, especially for organized supercells. Helicity values, which measure rotation potential in the wind profile, are extremely low given the weak shear environment. The lack of wind shear means any storms that do form will have difficulty maintaining organization or producing significant severe weather. The evolution tells us that today represents the best opportunity for storm organization in this forecast period, and even then, the shear constraints are limiting. In summary, Darwin's atmospheric setup today presents moderate instability with weak wind shear, the classic constraint for severe weather in tropical environments. While scattered to isolated thunderstorms are certainly possible, the ingredients for organized severe weather producing widespread destructive winds or large hail are limited. Always consult the Bureau of Meteorology for official forecasts and warnings. This analysis is provided by Distant Curve Remote Area Telecommunications. If you found this helpful, please like and subscribe to support continued severe weather coverage for remote Australia.